Hello, PyCon. Thank you for coming today. I'm Myles Scolnick. I'm one of the creators of Marimo, an open source reactive notebook written in Python. And today's talk is how we made the whole notebook, including the kernel, the package management, the event loop, run entirely in the browser using Pyodide. And so we're going to look at a few specific problems today that we hit during this migration and how we solved them, with the goal that you walk out of here understanding Pyodide a little bit more, running Python in the browser. Sorry, I see some special people in the crowd. Whether you want to run your own tools in the browser or learn a little bit more about Pyodide and WebAssembly. Cool. So why does this matter? Well, everyone in the room probably has a really good computer, so why would you want to just limit to running Python in the browser? Well, number one, accessibility. So a browser is a Python install. You don't need to open your terminal to install CPython. You don't need to set up a VM, no pip, no anything of that. Anyone can install it on anywhere, on any device. Number two, the cost. So notebooks just become the URL. You can stick the whole code right in the URL, up to 2 megabytes. You don't have to pay per user. This is big for education, big for documentation, open source projects, or anyone with a long tail of users. Latency, there's no round trips to a server. So this shaves off hundreds of milliseconds, so a lot of your code runs and feels instant. And lastly, as a bonus, it's secure. So it's secure by default. WebAssembly provides a nice isolation for you to run Python, doesn't have access to your file system, which can be really great for these new AI coding agents. For example, we run Pyodide in our own docs and on our own playground. There's a little demo. And I think in the last week, we served over 50,000 Marimo kernels just in Pyodide. So that's 2.5 million yearly Marimo kernels that are running in the browser without having to spin up a server. You could even run it in a refrigerator if you wanted to. This is not AI generated. I did make that, but it is not real. Cool. So I'm going to jump to a quick demo. All right. So this is the Marimo playground. And so Marimo runs locally, but it can also run in the browser. And so this is running in the browser, and I can show sys.platform. And so this is mscriptin. I can install a bunch of packages here. Some I can just import, some I'm using micropip. I'm going to quickly run through this demo, and then I'm going to touch on a lot of the stuff that I run in this demo. And so here in Marimo, I'm creating a slider, and I'm outputting the value of this slider and multiplying. So like you can see here, it's very instant, right? It takes 1 millisecond to run this, and this includes all the quote-unquote network latency. If you were running on a real server, this would actually not be as fast. I'm loading some data here in Art data set, which includes some embeddings. I'm loading over HTTP, so I'll talk about that a little bit later. I'm using a AnyWidget library called JupyterScatter, and so this allows me to plot this whole data set, and so this is something like 20,000 million points running in my browser, and so I can like zoom in and select some of this data, and so these are all different pieces of art, and it's a little bit hard to see, but here I'm rendering in a table, and I have this table of art. And so as I select new data sets, it all renders in here. And so this is all happening in your browser. There's no server, no nothing. And I'll come back to some of these points later. Now, how do I get back to? All right, just to quickly touch on a little of the terminology I'm going to be talking about today. I'm not going to go over this whole slide, but there's Pyodide. This is Python running in the browser. There's Python. This is just Python, but I may actually say this when I mean Pyodide or vice versa. They're kind of easy to get tripped up on. WebAssembly, this is just a format which allows you to run C, Rust, Python in the browser almost as quick as native code. Mscriptin, it's a compiler that turns C++ and C and Python into WebAssembly. Native Python or CPython, I'll be saying this a lot. This is just a normal Python that you're likely using day to day. A web worker, this is just JavaScript that runs in the background of a web application, so off the main thread. And if I say IPC, this is just inter-process communication. These are how two separate programs can talk to each other in native Python, so over threads and processes. Cool. So how did we get here? So Iodide was Mozilla's bet in 2018 on running scientific Python in the browser. In 2019, Pyodide came out of that project, which is CPython compiled down to WebAssembly using mscripten. And so those are kind of the words I was mentioned before. Pyodide also includes a whole package ecosystem, which is built on top of PyPy and a couple other special packages that are compiled especially to WebAssembly. And today, Jupyter and Marimo both build on Pyodide to deliver full notebook UIs that run in the browser with zero backend. So how did I get here? So Marimo was publicly launched back in January of 2024 by my co-founder Akshay. We launched on Hacker News, and in our original post, we had a few comments asking for Pyodide support. We did not initially support Pyodide, but it wasn't until a month later we came back to Hacker News and said we re-added Pyodide support to Marimo. So Marimo can run completely in WebAssembly and in the browser. So how did we do this in 1 month? And it's been an ongoing, like we have still made improvements, but how did we come back in that 1 month? So we refactored Marimo to support both runtimes, both native Python, also known as CPython, and Pyodide. And we're quite happy with the end result. We share the same kernel, the same parser, the same dispatch logic, and the same reactive engine. And Marimo runs in both runtimes differently. And so the boundaries between these were quite clear. I think only roughly 5% of the code base is Pyodide specific logic. And so what differs, you can see at the top, we have the transport. So it's still today, Marimo runs in a Starlet server, which is to serve WebSocket and REST requests. And Pyodide runs in a web worker and communicates over a window.post message. Our message queue went from multiprocessing to async IO. And our driver for the kernel, rather than being run in processes and threads, we're now run in a single async IO event loop. And the kernel is all shared. And I'm going to touch in a bit of these differences throughout the talk. So the first thing that we hit was running Marimo without a kernel, running the Marimo kernel without a process or a thread. So the native kernel runs in processes and threads. Pyodide doesn't support either. So we had to figure out a way to keep that same kernel semantics, but running in a web worker. In order to do this, we had to make the kernel more async friendly. And so in edit mode, Marimo uses a child process to spawn the kernel, and in app mode, we spawn them in threads. Both of these communicate over an interprocess queue, and so that's the multiprocessing queue. Subprocesses, threads, multiprocessing, all of those are unavailable in Pyodide. So we had to make the event loop async all the way down. We switched all the queues to async IO queues. We created shared protocols. And in the end, the final result was quite nice. We had interfaces such as a stream, a queue, a session, a consumer, and a bridge. And so each runtime implemented their own, and then we can just chain these all together. So this is kind of what the basic kernel looks like. You create some queues. These are messages coming in. You create some streams. These are messages coming out. You create the kernel. And then you just have a loop, a while true loop, just taking messages coming in, handling them, and then emitting messages back through the streams. In reality, it's a little bit more complicated than that. So in native Python, we run the kernel in a process, and we communicate over IPC. And then we also run the control queue in an executor, so we don't block the async event loop. And this keeps it free just in case other users wanted to create their own async IO tasks in their cells. And so comparing the native code and the Python or the Pyodide code, it looks quite similar. And so on the left, we're using a process and a queue to communicate over IPC. And on the right, in the Pyodide version, we're just using an async IO queue. And so we can await that directly, and we have the same while true loop. In the native code, we spawn it with a process, and in Pyodide, we just create an async IO task that runs forever. One other thing to call out, so we actually didn't support top-level await in Marimo initially. And it actually isn't as simple as just compiling down the code with this flag. We actually had to change the file format and a lot of other internals. But this is an interesting thing that, like, because we had to migrate to Pyodide and refactor the code base and support top-level awaits, and I'll get to why we had to support that, it was a nice thing to bring back to the native kernel. And so being able to support top-level await was actually quite useful in the native kernel as well. But the reason we had to support it in the Pyodide kernel is because Pyodide ships with a package manager called micropip, and the way you install these packages are micropip.install, and you call await on that. And so we had to support top-level await, so it was easy for users to install packages within their notebook, within their cells. Okay. So let's take a deeper look at this event loop. We had to remove processes and remove threads and change the Pyodide code path to be fully async. And just to build a little bit of intuition here, like browsers are based off JavaScript. They run a lot of JavaScript. Pyodide is trying to mimic running that JavaScript. And so the browsers are naturally kind of have this async code path. And so if you actually look at some of the async IO code paths and JavaScript code paths, they look very similar. And so I guess maybe historical Python code looked very like thread-based, and now it's maybe a mix. But I would say like browser code looks very similar to what async code in Pyodide looks like, or in Python, which is the async await syntax. So we had to move this to fully async. We replaced our HTTP server, that Starlet server, with a web worker. And that web worker sits between our main browser tab, which is our Marimo notebook, and the Pyodide kernel. And so the browser communicates through the web worker, or to the web worker, over window.post message. This is how it sends things back and forth. And so instead of over a WebSocket or over REST, it goes through a window.post message. And this gets queued up on one of our async IO queues using Pyodide's FFI. And so these messages that come in, these are message requests like creating a cell, run a cell, execute a cell, move a cell. And the messages that come out are things like the status of the cell, like what's the runtime state, what's the output, what are the console logs. So messages come in, the kernel processes them one by one in that while true loop we saw earlier, and then emits messages back to the front end. So the next problem we hit was handling interrupts. So native Marimo sends SIGINT to the child processes that it starts up for the kernel to cancel any running cells. This can be trivial in multiprocessing, but Pyodide, again, has no signals and has no processes. So how do you actually cancel these running cells? Otherwise, they'll just go on forever, and you're not able to use your notebook. So thankfully, Pyodide makes this extremely easy. Pyodide exposes a method called setInterruptBuffer. And so you can create this shared buffer, this 1 byte shared array that is created in the web worker, and then, created in the main browser. And when you want to interrupt from the main browser, you just flip the bit of that first byte to a non-zero value, and Pyodide will just check that value between byte operations, and if it's safe, it will raise a keyboard interrupt. You can't send a message to interrupt because it hasn't gotten to the next message to process. And so Pyodide and the main thread, or Pyodide running in the web worker and the main thread, they're in separate JS contexts. So you actually genuinely need to share this array buffer. You can't actually interrupt it otherwise. The next problem we hit, which came with a lot of other problems, making HTTP requests and downloading Python packages. So again, because we're in the browser, we can't use things that the request library uses or URL lib. They connect over sockets and TCP, and those things don't work out of the browser. So we had to convert everything to one, async, and two, work with HTTP requests. And package installation, there's a long list of things why not every package may work in the browser, but surprisingly a lot do. So I'm not going to go through this, but these are the types of issues that you may hit. And so native Python and Pyodide differ in many ways. The threading and processing model is different, as we saw earlier. The file system is slightly different. The networking is different, so Pyodide has limited networking or none. And most importantly, C extensions don't work out of the box when running in Pyodide. So there's a lot of differences that we had to work around. I would say the biggest takeaway from that last slide is there isn't a one-size-fits-all solution. Many of these came from patches, and so there's some open source patches like Pyodide HTTP, which will patch the URL lib library and request library. We've come up with our own patches to patch pollers to work in WebAssembly, and also DuckDB HTTP requests to work in WebAssembly. And we're actually exploring some more patches to work to mock out threading and things like that. For other cases, Marimo can intelligently render different outputs based on the support of the runtime. So for example here, choosing to load files over HTTP or sending data URIs. And so when you render an image in Marimo, we prefer to use HTTP when we can, then you get nice request headers. It can lazily load things. It doesn't have to clog up your DOM. Whereas in WebAssembly, because you don't have a server to serve these images, we just intelligently switch that to use data URIs instead. And so there's a few cases where this can be, it just happens all under the hood, and we don't actually have, like, as a user, as a consumer, you don't have to think about this sort of stuff. Another example of this, so there's a Marimo utility called notebook location. And so in native Python, you'll get the directory, whereas in the browser, you'll get the HTTP URL. And so again, these sort of utilities allow you to go seamlessly from running locally to running in your browser. And you don't have to change your code at all. And so, for example, in this case, if you have a public folder with data.csv, and then when you publish it, that stays in that same public folder, you can access both these files using this kind of same trick, notebook location /public/data.csv, and so your data frame will seamlessly load the data in either context. Okay, so I said in the initial slide, blazingly fast. So how do we actually make this performant? And I'll share some tips and tricks that we've implemented to make this runtime feel very fast. So number one, a custom Pyodide build. So since Pyodide and all the packages get loaded into the browser, the size of the package does matter. So we trimmed down Marimo's wheel to exclude non-relevant files. So files that only made sense when running in a server. This can reduce the build size by about half. A custom lock file. So we serve a custom lock file so we don't have to hit py every time for the core dependencies. This means that we could load the wheels directly without needing to transitively resolve all the dependencies, which in the browser is actually worse because you get these sort of waterfall effects, and trying to stat solve what versions are compatible. Sorry, I'm just going to have a sip of water. The third thing we did was reveal in the editor before the kernel was ready. So as soon as we have some code to show or some outputs, we show that while we continue to load and initialize more of Marimo. And so that kind of gives the user the feeling that they can actually start typing, and even though the kernel's not ready, they can actually make some progress and then hit run, and it's going to be ready by the time anyways that they want to hit run. Number four, loading initial dependencies in the background. So kind of similar to like initializing Marimo in the background, we also load dependencies. And so we grab dependencies either from the import, so we'll scrape the imports of each cell if you've already written to the notebook. We'll also grab dependencies from the PEP723 metadata, so if that's in the header, we can load those in the background while Marimo is starting up. You could also have multiple web workers. And so I showed one web worker, and that's just processing the kernel. We actually have another web worker that we added later to auto-save the code in the background. And so if you had one web worker, then you wouldn't be able to save while a cell is running. And so this allows us to save in the background while also another cell is running. And lastly, something we tried but skipped was creating heap snapshots. So Pyodide has support for snapshot in the heap, which means like after you run some code or import some Python modules, it can snapshot the memory. And so you'll kind of have the post-import view of what your world looks like, and so you can snapshot that. But you have to store that somewhere, and so that does hit a network cost. And so we found the network cost did not pay off compared to the startup cost, so it was something we did not do for our case, but something that may work for your use case. Some other improvements just came from following browser best practices. So I wouldn't focus too much on these numbers because they vary differently based off network, your own Wi-Fi speed or how many packages you're installing. But generally, you can expect after the first load, your network costs go to 0. And so the rest of the costs you're paying are around disk reads, decompression, parsing, module graph resolution, and any other setup that WebAssembly may hit. Okay, to summarize some of these learnings into 4 takeaways. The first, feature detect at the boundaries. So check what platform you're running in, at least in our case, checking that we're running in Emscripten, and avoid sprinkling these conditionals throughout your code base. So checking at the boundaries is much cleaner. Prefer composition over inheritance. So using parallel classes and not subclasses and create shared protocols like we saw before. So like our stream, our kernel, our queue, creating these shared classes, and then kind of pairing this with feature detecting the boundaries. So we check if we're in Pyodide, create these shared classes, and then everything else downstream is quite clean. And I think these are general tips that anyone should use when building any library. Number 3, prefer async primitives that work in both runtimes. I think this simplifies a lot of code, and you can always optimize later. So using async is fine. It works in both runtimes, and then as soon as you need multiprocessing, you can sprinkle that in later as needed. And then lastly, abstract away OS-level concerns. So things like threads and signals and processes like we saw before, and your file system if possible. Okay. Of course, what is a technical talk without an ending slide with some caveats and limitations? So a couple things to note before making your package compatible with Pyodide. There are some limitations. So number 1, there's a memory limit. Chrome, I think, gives you 4 gigabytes in your tab, but Emscripten currently limits you to 2 gigabytes. I think there is some work to make that more, but for now, yeah, you're limited to 2 gigabytes. And that's not just your packages, but also the data running through your stuff. So if you're crunching large amounts of data, you may hit this limit at 2 gigabytes. Are you pure Python or your depths pure Python? So Emscripten running through Pyodide requires you to either have a pure Python wheel or to compile your C code or Python code down to WebAssembly using Emscripten. And so that's true for you and your dependencies. But Pyodide does support a lot of packages that have already done this for you, and a lot of the SciPy packages like NumPy, Matplotlib, and Polars, PyArrow, and Pandas, to name a few. Those are some common ones that we see. So those all work in Pyodide today. So if you depend on those, you will probably be okay. And lastly, if you use threads, then Pyodide may not work for you. But if you can convert it to async, like in our case, then you can definitely use Pyodide. And so if you just need quote-unquote concurrency, you can definitely achieve that with Pyodide and async I/O. Awesome. So if you have one takeaway for this talk, it's this, that running your code in Pyodide or in a browser-compatible notebook such as Marimo is way more accessible than people assume. And so you can test this today. If you go to marimo.app and just put your package in there, Marimo will try to auto-install it, and you can see if your package is compatible. If not, you can use some of these learnings to make it compatible. You can check out our repo. And this is a QR code, which is just an app to make a QR code because I ran out of creativity. So this is a Marimo notebook that you could run on your phone, just to actually show that you can run Python on your phone installed in your browser. That's it. Thank you.
Okay, so we have about 6 minutes for questions, so please line up in front of the microphone right there if you have any questions, and we can see if Myles can answer some of them. Okay?
Hey, thanks for the talk. What's a good way to find out what packages are available to install? Like, if you have, if a package has been compiled for WebAssembly for Jupyter, does it automatically work in Marimo because it's WebAssembly, or is there a special curated list? And
Yeah, so there's probably multiple sources right now. Like on Pyodide's website, they have a list of packages that they've compiled themselves. If you know your package just works in Jupyter or JupyterLite, then it should also work in Marimo. I think the best way is just trial and error, so just install it. If you just do like import and then my package, it will prompt you to install it, and you can see if it works. Even though it can install it and it is Python, you still may use Python modules that aren't supported. So if you're using things like sockets or SSL or any of the threading like I mentioned.
okay, thanks.
Hey, I'm not a front-end developer, so sorry for a newbie question, but do I get it right that with Pyodide, it's possible to run on front-end Python script instead of JavaScript?
Sorry, say it again. To run on?
To run in browser on the front end, like Python instead of JavaScript or TypeScript.
I am running Pyodide in the web worker. You could just run it pure on the main thread in the front end, but that does block things, and so that's why we put it into the web worker, because it does give you like a separate thread that it won't block the main thread, which is in charge of rendering UI and yeah, HTML. So if you have like React that's also running it, it will like slow down and kind of seem a little janky to maybe your users.
Mm-hmm. Got it, thanks.
So I had a question about, that was based mostly about when you talked about how second processing is done. So my question basically is that would you need to have, like second is like one signal that you know what to do, like you can kill that particular cell. But if your Python program is doing something more complicated with signals or like doing a bunch of IPC or something, does your web worker have to, like, does your web worker have support for that, or is that something that will be patch by patch basis?
Yeah, signals wouldn't work either, and this is probably true of any signals, but I think the Async IO module has like events that you might be able to leverage. But that's a good question. I don't know entirely. You could still send, so SIGINT is just for interrupt, but if you're sending signals or messages, you can still send, like if there's nothing blocking the main thread, or like the thread that's running like the kernel, you can still send messages and like custom messages as needed.
Okay, thank you.
Hi, is there a way to install packages from a private repository, a private index, like Artifactory?
Yeah, so if you use, in our notebook, we don't support like a default index, but if you use micropip, you can just use a full URL, and so you could just have like HTTPS all the way up to your .wheel, and install from there.
Do you know if it supports authentication?
That's a good question. My guess is probably not.
Okay, I tried a couple
I can look,
couldn't
yeah.
get it to work.
There may be a second argument in micropip that allows for it. I'll have to look at that.
Made enough